Welcome back, everyone. So this is going to be a video lesson about exponential functions. And you're probably thinking, we already know about exponential functions from pre-calculus and algebra. This is going to be about derivatives of exponential functions, which we haven't exactly done yet. Okay, so let's go ahead and get started. So, derivatives of exponential functions. I think for a few minutes, what I want to do is just remind you some things about exponential functions in general, because this is going to help us. So recall, if you're given a number a that's greater than 0 and a is not equal to 1, the exponential function with base a is f of x equals a to the x. All right, so that's just the definition of an exponential function. And this is kind of two definitions in one because it tells us what an exponential function is, and it also tells us what this word base means. The word base is just used to describe this number a. And of course, note, this is not to be confused with x to the a. If it were x to the a, then we would already know how to differentiate it, right? Because we had a different derivative rule for x to the n. So if you have x raised to a number, we already know how to do the derivative. But if it's a number raised to the power of x, that's what we need to talk about today. So let's remember what the graphs of exponential functions look like. When you first learned about exponential functions, you probably saw that the graphs can be thought of as two different cases. So let's draw two different pictures here. This is just a quick review. We could set up the scale like this. And the first case is the exponential function a to the x when a is greater than 1. And those graphs tend to look something like this. Of course, the exact picture depends on exactly what base it is. If you have 2 to the x, that's going to look different from 10 to the x, but they'll have the same overall behavior. It's just that 10 to the x would increase much more rapidly. It would go kind of steeper, but it would still have the same y-intercept of 0, 1, right? No matter what base you have, no matter what a is, what is a to the 0? Like if I did 2 to the 0, if I did 3 to the 0, whatever the base is, when I raise it to the 0, I'm going to get 1. So I know that it passes through this point. One other feature that I will maybe do in blue here is there is a horizontal asymptote on the x-axis. So the graph approaches that line but never quite touches it. Over here, if we talk about the other case, that's going to be y equals a to the x. Again, this is just a quick review before we get to the derivative part. The other case is if a is between 0 and 1. And remember, from the definition of exponential function, the base has to be positive, and it can't be equal to 1. So these are really the only two cases you could have. Now, it's still going to have that same y-intercept because a to the 0 is still going to be 1. It's still going to have this horizontal asymptote because there's nothing you could do that would make a to the x be negative. But instead, the graph is going to look something like this. Something like that. Now, out of these two cases, I will admit that the first case is much more common. I think that we often think about exponential functions as being curves that grow very rapidly. And we talk about things like, interest. So, your amount of money is increasing. Or we talk about things like population growth, and you think population is going up and up. But this type of exponential function is also useful. This is sometimes used for things like radioactive decay, where you have something that's getting smaller and smaller over time. So they both have their uses. Well, I guess what we want to say for now is that it certainly looks like these functions should be differentiable. It certainly looks like I should be able to talk about the slope of the tangent line, right? I don't see any weird vertical jumps. I don't really see any discontinuities, right? So let's talk about some properties. Properties of f of x equals a to the x. And I'm talking about both cases now, all exponential functions. First of all, the domain is all real numbers. Okay, you can put in any number you want. A to the 1, a to the 2, a to the 3, a to the negative 10. You know, x is allowed to be negative. X is allowed to be 0. You know, x can be any real number. The range, you can tell from the pictures above that the range is 0 to infinity, right? We have everything above the x-axis. Y values are above 0. They both have a horizontal asymptote, as I mentioned, at y equals 0. And I'm going to say that they are both continuous and differentiable on the set of real numbers, on the entire interval from negative infinity to positive infinity. Any x value you want, you take a look at any x value you want, and this curve will be continuous and differentiable. So that's good. We like functions that are continuous and differentiable in calculus. Now, one thing that you may have learned is that different exponential functions pass through the y-intercept with different slopes. All right, let's think about this sentence. All exponential functions pass through that same y-intercept of 0, 1. But depending on what the base is, you'll get a different exponential function. It could be 2 to the x. It could be 1/3 to the x. But whatever it is, it's going to pass through that y-intercept, but it does so with a different steepness, a different slope. And when I say slope, this is a curved line. So when I say slope, we're really talking about the slope of the tangent line. And I'll show you two little examples here. Both of these examples are going to actually be from case 1 up above. All right, let's say this is that y-intercept. Let's see if I can draw these the way that I want. All right, so I'm trying to draw here approximately a picture of y equals 2 to the x. And this one is going to be approximately a picture of y equals 4 to the x. So this is what I meant a few minutes ago when I said that different bases have the same overall curvature, the same overall shape, the same y-intercept, but the larger the base is, the more steep the curve is, the more rapidly it increases. So let's talk about the slope of the tangent line at the y-intercept. I think that in this picture, it looks something like this. The tangent line. And I don't know, we could try to estimate what that slope is visually, I guess, but let's just say we drew the tangent line and we want to compare it with this one. They're pretty different, right? And I don't know, I mean, just based on this picture, I guess I would say that the first picture, it looks like the slope of the tangent line is, what do you think? It's less than 1, because a slope of 1 would go up 1 unit for every 1 unit we go to the right. So a slope of 1 would look like a 45-degree angle, kind of. And this looks like more like maybe a slope of 2/3 or something like that. It looks to me like uh, it's less than 1. Over here, if I were to try to figure out what this slope is, well, we didn't really label points on the x-axis and y-axis. We weren't really very thorough with this. But, you know, I would say that this slope is somewhere less than 1, and this slope is somewhere greater than 1. Maybe this slope looks like it might be 3 or something like that. Or 4. I don't know. Anyway, that's just 2 examples of different exponential functions passing through with different slope of the tangent line. Well, did you know that there is one base called e such that the slope of y equals e to the x at 0, 1 is exactly 1. Yeah, that's the base that we're most interested in, I guess. That base actually would look, let's see here. I'll try to make this picture a little bit more accurate. So this one we'll go ahead and label all right, looks something like this. Y equals e to the x. And the tangent line at the y-intercept would have a slope of exactly 1. Slope equals 1. You see that it's making a 45-degree angle with the x-axis? If you take the tangent line and the x-axis, you get a 45-degree angle. So for every 1 unit I go over, I go 1 unit up. And e, the number e, is a constant that's approximately 2.7. And some other digits. You've seen this before, but we're just reviewing it. This is also known as Euler's number. So this description here of the number e, this is actually one of the ways that you could define the number e. There are different ways to define it, but you could define it to be the base that has a slope of the tangent line equal to 1 as it passes through the y-intercept, because there's only one base that does it, and that's this number. When we think of it as a number, we say it's an interesting number, but when we think of it as a function, we say it is called the natural exponential function. That's a pretty powerful name. That seems to suggest that there's something natural about this, and that it's sort of the almost like the default exponential function. Out of all the bases that you could possibly have, this base actually shows up a lot in math and science. I'll tell you another way to define e. Maybe you look at this and you say, like, well, that's kind of weird defining e based on the slope of the tangent line and stuff. Well, another way, like, we don't want to define e to just say e is some number that's around 2.7 and it has special properties, because that's not very precise. That's kind of vague. And you can't actually list out all the decimal digits of it. This keeps going on forever and ever with no repeating pattern. So we can't pinpoint, we can't write out exactly what it is. It's kind of like pi, where the decimal expansion goes on and on forever. And it's been proved that it goes forever. It has no repeating pattern, never stops, and never gets into a repeating pattern. Anyway, another way to define e. Oh, I guess, you know what? That kind of raises an interesting question. We're talking about two different ways to define the special number e. How would you define the number pi? Like if somebody asked you to write a definition of the number pi, I guess you could define it in some way in relation to circles, but there are other ways to define pi also. We know from trigonometry that pi, you might be able to define it in terms of triangles and angles, or you might be able to define it in a way that doesn't involve those shapes at all. Anyway, we're working on e. E happens to be equal to this limit. The limit as m goes to infinity of 1 plus 1 over m to the m. Now, this is not a formula that you need to memorize or anything like that, so don't worry about that. But this is an equal sign. This e equals exactly this quantity. Is that a weird-looking expression? I mean, m goes to infinity, so the thing that's in parentheses, 1 plus 1 over m, as m goes to infinity, the part that's in parentheses looks like it's getting closer and closer to just 1, because the 1 over m becomes insignificant. 1 over a million, 1 over a billion, right? So the thing in parentheses is approaching 1 from above. The exponent is approaching infinity. So you have something approaching 1, something approaching infinity, and I'm saying that this limit actually equals exactly e, which is somewhere around 2.7. So this definition here is kind of tricky, and we are not prepared to prove this. We might revisit this limit later in the semester when we talk about something called L'Hopital's rule. But I don't know. I think both of these types of ways of defining the number e, both of them are a little weird, but I guess the number e is a little weird, so it just works out that way. All right, now we've spent a page and a half on kind of a quick review of exponential functions, and we've defined where this number e comes from, whether you like the first definition or the second definition. And we actually talked a little bit about slope of the tangent line. So far, I think based on what we've said today, we could definitively say that if f of x equals e to the x, then we at least know f prime of 0 equals 1. Do you agree that we've already said that? Like, I think we've already said that today. Right up here in the sentence at the top of the screen. We said that if the function is e to the x, the slope of the tangent line at x equals 0 is 1. So that's what I wrote here. F prime of 0 equals 1. But that's f prime of 0. That's the derivative at a specific point. And we would like to know more generally. What if f of x equals e to the x, and we ask ourselves, what is f prime of x. And by this, I mean we want a formula or rule. We want to derive a formula for the derivative function of e to the x. We already have a bunch of derivative rules, shortcuts, formulas, but a lot of them are for things like polynomials, square roots, things like that, and we need to kind of come up with something new for this situation. Okay, so here's what we're going to do. Because this is a different type of function, I don't think we can use our polynomial shortcuts or anything like that. We could always go back to the definition of the derivative, right? The limit as h goes to 0, f of x plus h minus f of x over h. Now, I know lately we've been trying to avoid using the definition of the derivative. We've been trying to use shortcuts instead, but we're trying to find a shortcut right now. So we'll use this and we'll do some steps, and we're going to basically come up with a rule. Once we come up with the rule, then we'll always be able to just use it. All right, so let's set this up with this function. So the limit as h goes to 0, f of x plus h in this case is going to be e to the x plus h. F of x is e to the x. What do we do with this? Usually when we use the derivative definition formula, usually we start trying to rearrange it and look for things that cancel. Look for things we can expand or combine or cancel or whatever. So here's an idea. Let's rewrite, instead of e to the x plus h, we have a rule of exponents that says we could call this e to the x, e to the h. And that is the same thing. Now, does that help us? I mean, now we could see that in the numerator, both of these terms have e to the x, so maybe it's tempting to pull e to the x out, and then you're left with e to the h minus 1. We don't really have anything that I can cross out yet, and we don't have like an h over h or anything like that. I'm going to use a property of limits. There's a property of limits that says we can split this up into the limit of e to the x times the limit of the other part. See what I did there? Back when we talked about limit properties, we had one for the limit of a product. It can be split up into the limit of each piece. And up here, you know, this numerator was a product. It was e to the x times the rest of the function. So let's look at each one of these pieces separately. This and this. For the first piece, I think as h goes to 0, e to the x is just going to equal e to the x. Because it's not, you know, we could put an equal sign here if you want. Because it's not x that's going to 0. It's h that's going to 0. So e to the x is still just e to the x. What about this other stuff over here? The limit, h goes to 0. Is there, you know, do you think we need to do some kind of rearranging here and work on this? There's not really much we can do with it. All right, so I'm going to show you a cool little trick, is that this expression is actually equal to f prime of 0. Because, maybe think about it for a second, see if you can see why that's equal to that. It's because f prime of 0 would be the the limit as h goes to 0 of f of, I guess, 0 plus h minus f of 0 over h what would we have? E to the h minus e to the 0 over h. I'm going to put this in parentheses. It's kind of a side note. So this part of it just equals f prime of 0. We said that this equals 1. We said that above, right? F prime of 0 equals 1. It's still on the screen. It's still up here on the page. So what did we get? We did f prime of x. We did all these steps. Ultimately, it looks like it equals e to the x times 1. So the result, the rule that we've been looking for, the derivative of e to the x is equal to e to the x. E to the x. It's e to the x times 1, but we don't need to write times 1. So that's pretty cool. We just derived a new rule, and the rule itself is very easy to remember. Anytime you have to do a derivative of e to the x, it just equals itself. And I think this is the first function we've seen. Well, it's kind of the first function we've seen that equals its own derivative. I'm going to say that this equals, its own derivative at any real number x. And this is basically the only function that does this. Equals its own derivative. Why did I say it's basically the only function that does this? Well, technically, there are other functions that also equal their own derivatives. Can you think of any? Can you think of any? E to the x equals its own derivative. Also true for any multiple of e to the x. So that's why I said this is basically the only function that equals its own derivative. Like if we had to do the derivative of 2e to the x, that equals 2e to the x. I'll just say etc. Okay. By the way, 0 also counts as a multiple of e to the x. The derivative of 0 e to the x equals 0 e to the x. That also works. All right, so we've established this rule and we derived it. And we don't have to derive it each time we use it, of course. We can just go straight to this rule and use it as a shortcut. And best of all, we can combine it with other things that we've already learned. Because I don't think you're going to get a problem that just asks you, what's the derivative of e to the x? That would be too easy. Instead, we're going to give you questions that combine it into other functions. So here's an example. I'm going to ask you to differentiate. And I'll give you two parts. Part A, f of x equals 3e to the x minus x to the 3 plus 7. And part B, g of x equals e to the x plus x to the e plus e to the 2. So I'd like you to take a minute and try both of these and maybe pause the video and give it a shot. All right, so let's work on these right here. So solution. Remember, we don't have to use the definition of the derivative formula or anything like that. The derivative of each piece. So the derivative of 3e to the x is 3e to the x. The derivative of x to the 3 is 3x squared. And the derivative of 7 is nothing. It's 0, right? Because the derivative of a constant is 0. So we just leave it like this. And I'm going to say that for this one, you could leave it like this, or if you wanted to, you could pull 3 out. Either way is fine with me. Part B, I guess part B is a little weird looking. I did that on purpose. This is trying to trick you, or it's trying to make you be careful. I guess that's what I should say. In part B, you need to be careful. So what is g prime? Derivative of e to the x is e to the x. Let's just do each piece, right? I'll put a plus sign. Okay, what's the derivative of x to the e? X to the e. Well, I said at the beginning of this lesson that we already know a derivative rule for x raised to the n. We know x raised to a number. We know what to do for that. You take the number, you move it out front, and then you have x raised to the 1 less than whatever the exponent was. All right, I want you to keep in mind, I want you to remember that e is just a number. E is a constant. It's around 2.7, right? So when you see x to the e, you could think of it kind of like x to the 2.7. It's not exactly 2.7, but that's close, close enough for this conversation. Yeah, so when you see x to the e, just think x is being raised to 2 point something. You move that number out front, and you decrease the exponent by 1. All right, last piece, e to the 2. What's the derivative of e to the 2? It's nothing. It's 0, because e to the 2 is a constant. This is like 2.7 something squared. And that equals, what, 8 point something? I don't know. It's some kind of constant. When I take the derivative of it, I get 0. So we're done. That's the answer. So yes, it was a little weird looking, and I'll admit that something like x to the e probably doesn't show up that often. It's a little bit of a unusual function, but here we go, we did it. Okay, so what else do we need to talk about? Remember that this section was called derivatives of exponential functions, and you might say, wait a second, we've only talked about the derivative of one exponential function. We've only done this for one base. We've done this for the base e. We established a rule, but what about other bases? Even if we say that e to the x is a very common base, a very natural base to use in math and science and engineering and stuff like that, there's still other bases. What if it were, 2 to the x, 10 to the x? In general, what is the derivative of a to the x? Now, basically, this is a harder question, and in the textbook that we're following along with, other bases are actually not discussed in this section at all. But I thought, I would be doing you a disservice if we just said, okay, let's call it a day. I think that this is the section called derivatives of exponential functions, and we should at least address what about other bases. And I'm going to tell you the answer for now. It's not just a to the x, it's a to the x times something. It's going to be a to the x times ln of a. Now, this rule, which I have not proved to you, I have not derived, I'm going to tell you that deriving this requires a rule that we haven't covered yet. It's a rule that's called the chain rule. So when we get to the chain rule, we might come back and revisit this idea and see where does this formula come from. But for now, I wanted to at least show you this briefly. For example, the derivative of 2 to the x, that is an exponential function with base 2, and its derivative is 2 to the x times ln2. And by the way, ln2 is just a number, right? ln2 is just a constant. It's a number. You could actually move it to the left, put it out front if you want, or you could leave it here. I guess another common base is base 10. So this would be 10 to the x ln 10. What if we try this formula? What if we try this with e to the x? Now, let me be clear about what I'm doing here, or what I'm about to do. We already said a formula for the derivative of e to the x, so I already know what it is. Okay, I already know that the answer is supposed to be e to the x, but I want to look at this this second formula, and I want to say, you know, this is supposedly going to work for other bases. Does it actually work for any base a? If it's going to actually work for any base a, then it should also work for e, if it's really going to work for any base. So let's try using the second formula. I guess in this case, a is equal to e, so I guess we would do e to the x ln e. Is that the answer? Well, yeah, actually, look at this. ln e is equal to 1. So this does get us e to the x, which is what we were expecting. So what's the point of this last thing, this last sentence here? What's the point of this? What I'm trying to show you is that these two formulas, they are compatible with each other. There's no conflict. It's not like we need some special exception or something. It's that this second formula does in fact work for any base a. It could work for base 2, it could work for base 10, it could work for 1/2. It works for e. It just adds an extra little step, but it does still work. That's all I wanted to show you. In math, our rules should be consistent with each other, and when we come up with a new rule, we want to make sure it doesn't break anything about our older rules. All right, so those two little examples that we did up above, you might see some problems like that from this section. So you should be ready for that. So this section turned out to be a little bit shorter than some of the other ones. We really just reviewed exponential functions and what the number e is, and we established a derivative rule for e to the x, and then we briefly discussed the derivative rule for a to the x, but I said that we might revisit that a little bit later. So the next section that we do, the next section is going to be very important. And we're still going to see more practice problems with exponential functions. It's just they're going to be combined with other things that we're going to discuss in the next section. So that'll all make sense in the next video. All right, so make sure you watch the next one. It's going to be a really important one. And that's it for now. I'll see you all later. Bye.